So this is Physics 1C for, what is today? Tuesday, April 20th, 21st. Today we're talking about these 5 things. Force between parallel wires. We're going to learn about a new one of Maxwell's equations, which is called Ampere's Law. And we're going to apply Ampere's Law to a solenoid, to a toroid. We'll talk about what those are. Solenoid is basically a tube with wires wrapped around it. A toroid is a donut with wires wrapped around it. Okay, and I think the word torus means donut, right? And then the final thing we're going to do is we're going to talk about the magnetic flux through a loop near a wire. And this is going to kind of set us up for what we'll be talking about next, which is what's called Faraday's Law. So actually, we're going to have all of Maxwell's equations this week. We're going to be done with Maxwell's equations, at least in one form. We're going to expand upon them a little bit, but that's kind of neat that we'll be done with. We'll have kind of all the rules of electricity and magnetism at our fingertips by the end of this week. So this is your setup, okay? And I'll draw my own setup too, so like it's clear what's going on here. So the idea is, this is you have 2 wires, okay? So I draw one wire like this, and I say that it carries a current that we call I1. And then below it, but parallel to it, I draw another current, and I say it has a current that we call I2. And the question would be, what's the force that one wire puts on the other wire? Now, why would there be a force? Well, there's a force because we learned that there's this thing called the magnetic force, right? And the magnetic force applies to 2 different situations, okay? One of them is, suppose I have a charged particle, right? And say it's moving in space with a velocity v and has a charge q, right? And if it happens to be placed into a magnetic field, like let's say, for example, we have a magnetic field in this region of space that goes into the page like this. Okay, say we have a magnetic field just like that. Then there's going to be a force on this charged particle, and maybe some of you guys can tell me what direction does that force point. It's given by this equation. The force is given by, you guys said up? Yep, I agree, it's up. The force is given by QV cross B. Velocity cross with the magnetic field, cross product, and that gives you the magnetic force, and you multiply by the charge. If the charge is negative, you flip it upside down. So as you guys said, yep, you're right, there's a force that goes up this way on this particle. That's the direction of the force. But that's not the only type of magnetic force that can exist, because if we replace this moving charge with a wire that carries current, which is effectively the same thing, right? Then you get the same effect. So in this position right here, let's say that I place a current carrying wire right here, and then just extend where the magnetic field is. So if I have a wire that carries some kind of a current, and we call that current I, and the wire has a length that we call L, right? I'll use this color. If the length of the wire is L, and you draw a vector to represent this, whoops, you make a vector to represent that right there. Someone's mic is like picking up tiny little things right now. I'll figure out who it is in a second. All right, so given those, then you find that there's also going to be a magnetic force on this wire right here. And you can probably figure it out just by looking at the picture above, but what direction would the force on this orange wire here be? You guys want to answer? What would the direction of the force on this wire right here be? Yeah, downwards. If a charged particle moving to the right experiences a force that's up, a current carrying wire, which is full of charge carriers, must experience a force that points downwards. Using the same color as before, the force on our wire here is going to point down like this. And it's going to be the whole wire that feels the force, so we'll draw a couple errors for that, but that's the direction of the force then. And the size of that force is given by a similar expression that involves current, and then you have to do times L crossed with the magnetic field, okay? That's one of the things we learned last time, right? Does anyone have any questions about that? Because that's what we're going to use here to talk about the situation. Now, the other piece of like theory that we had from before that we need to add into this is that we also know that if you have a current carrying wire, okay, so if I have any wire that carries current, I, if I come to some distance away from the wire, like if I move some distance like here that we call R, then at this location right here, there's going to be a magnetic field that points into the page, and the size of that magnetic field is going to be equal to this mu naught, which is just a constant, times the current divided by 2 pi multiplied by the radius, the distance to this point. And the field is going to point into the page here, and it's going to point out of the page up here. The field's going to get weaker the farther away you go. So this is the theory. This is kind of what we've been developing over the last like 2 weeks, right? 2 weeks ago we derived this stuff, and then last week we were talking about this stuff, right? So maybe the other way around actually. I think we went in this order. I think we did this first, and then we learned how to do this second, right? But now what we can do is we can put them together, okay? Anyone have any questions about all that kind of like background stuff that we've been doing before? Okay. So let's look at this problem. I take two wires, I1 and I2, different currents, and I want to say that they're separated by some distance, and we'll use the same thing as in this picture right here. We're going to say that the distance between these two guys is going to be A. Look at that, the line's so straight. And the first thing we're going to do is say, well, if I've got a wire I2 right here, it's going to produce a magnetic field up here, where the location of I1 is, right? There's going to be a magnetic field created by wire 2 at the location of wire 1. Can you guys tell me what direction is it going to point? What direction is the magnetic field at this location, where that little orange dot is? Is it going to be out of the page or into the page? The magnetic field created by wire 2. Hope I'm on the right channel. What does everybody else think? What's the direction of the magnetic field right here? Created by wire 2. Is that question unclear? I can clarify if you guys want. Okay, what do other people think though? Can you guys just take a guess, maybe? It's 2 options. Yikes. Nothing. You guys here? So how do you know that? Someone want to explain? How do you figure it out? No, you can tell. I prefer you open your mic, but typing is fine too. Yeah. Yeah. How would you apply the right hand rule in this situation? That's what your right hand would look like, right? That's what you're saying? And then the direction that your hands would curl would be like this, right? Kind of around the wire, right? And that's basically what happens is you get this circular magnetic field that points around the wire like this. Can you guys see how your hand naturally rotates in that same direction? Do you guys see what I'm saying? Your hand naturally you point your thumb along the wire, and then your hand naturally rotates in the direction of the magnetic field. So at the location of this guy right here, the field has to be coming out of the page. Okay, it's actually a dot, exactly as I drew it right there. There's going to be a magnetic field right here that's going to be coming out of the page at every point along this wire right here. And that field we're going to call B2. I don't know if you can see it in this picture here, but that's pointing out of the page, right? It's the same setup as what we have here. And then if you look at this diagram right here, right, you've also got at the top right here, these dots mean coming out of the page. I don't know if you guys remember this, but this means out of the board, and this means into the board. And the way to remember it is you think about this one as an arrow that has like feathers at the end, right? And when it's that's awful. Has feathers at the end, and when it's going away from you, you see the tail. When it's coming towards you, you see the dot. Anyway, does that make sense to you guys? It's kind of a really important part about understanding this is being able to see these things. Does anyone have any questions about that? I won't be able to erase that one, I guess. Okay. So, at this location, there's going to be a magnetic field that we call B2, and it's produced by this wire that carries a current I2. And then we can use that equation there to describe the value of B2, right? B2, the magnetic field at this location, all along this wire, it's a distance a away, and that a is going to be this r that shows up in the denominator right here for this equation. So we can say that B2 is going to be equal to mu naught multiplied by the current, which in this case is I2, and then all of that divided by 2 pi multiplied by a. That's the magnetic field at that location, basically. And here's the three-dimensional version of it here. Anyone have any questions? All right. The next thing we need to draw in here is the length of the wire, and we're going to draw it as a vector. The length of the wire we're going to call L, and we're going to have the vector point in the same direction the current's flowing, right? And then we're going to say, I can find the force on this wire now by using this equation. The magnetic force is the current in the wire, right? So this is going to be, I'm going to call this the force of, we'll call it F1 as it said right here. The force F sub 1, okay, is going to point downwards. Like this, on the wire. And the reason why it points in that direction is because of the right-hand rule. You point your fingers in the direction, the fingers of your right hand in the direction of L, and then you rotate to B, which is out of the page, and then your thumb should point down. Hopefully you guys can all see that. That if you take the fingers of your right hand, you point them so that your palm is away from the screen, so that you can rotate from the current to B, your thumb points down. Can you guys see that? Have you guys gotten like comfortable enough with the right hand rule? This is the part of this where I feel really awkward. Like I need to see your hands and stuff to see that you can show me that you're doing this. But can you guys all verify for a second why this force is down here? And if you don't understand, I can try to draw something on the screen. So if this is your hand, if you face it so that your palm is up, so this is your palm right here, right? You face it so that your palm is up. You point your fingers in the direction of L, right? So L points like this. Oops. L, right? And then you're going to rotate your fingers up to the direction of B, and B is pointing out of the page, right? That's the direction of B, is out. So can you see if you go from L to B that your thumb has to point down, and that gives you the direction of the force. Does that picture make sense, what I'm drawing there? Like in terms of how your hand would be oriented? In this case, you actually like have to kind of twist your hand a little bit to make it work. Do you guys understand? Is there anyone that doesn't understand? I know it can be difficult to ask, but I'd be happy to explain it again if I can. Just say in the chat or something if you don't get it. Okay, this right-hand rule stuff is basically the only thing you're supposed to even learn in this class, to be honest. So if you're not getting it, you need to talk to me, and you need to ask questions. So getting back to what we were doing, the force 1 is the force of basically wire 2 on wire 1. And according to our equation, it's equal to the current that's flowing in that wire, which in this case is going to be I1, multiplied by the length, and then cross product with the magnetic field, which basically means you multiply by the magnetic field, and then you multiply by the sine of the angle between the two of them, which in this case is 90 degrees, okay? But the magnetic field that we put here is going to be the magnetic field that's created by the other wire. Wire 1 can't exert a force on itself, right? So it has to be the magnetic field created by wire 2 that's actually producing the force. And in terms of the direction in this case, well, let's leave that part off because you can see the direction from the picture. Wait, why is it not? Alright, so that's our force. And we can put the two equations together now. So we take this equation here for B2 and we plug it into this equation here. So now what we end up getting is that F1 is going to be equal to I1 times the length times B2. And B2 is equal to, from over here, mu naught times I2 divided by 2 pi a. And then sine 90 is 1, right? And now what we can get now is if we rewrite it in the following sense, I can write the force per unit length is equal to mu naught multiplied by I1, multiplied by I2, and then divided by 2 pi a. And that is the force between two parallel wires per unit length. And we can make the following statement. This force is attractive when the wires carry current in the same direction. And then you can probably figure out pretty quickly here that if you change the direction of the current so it was flowing in the opposite direction, what would happen to the force here? If the current goes the opposite direction, what happens to the force? Can I rotate on this thing? It should flip, right? Up the other way. Can I rotate? Does anyone use this programmer very often? What bottom box? No. that actually would have made a lot of sense. I know you can do it in Paint, but basically just imagine if we change the current direction, you need to rotate this diagram by 180 degrees, right? Because your palm is going to be going to the left, and now your thumb is pointing up, and that tells us that if the the force is going to be up at that point, right? So the same direction if the force is attractive, but it's going to be opposite directions. Oh, sorry, if the current is in opposite directions, then the force is repulsive. Maybe that's not clear. Same direction, like for the current. So if the currents flow in the same direction, you're going to get an attractive force. If they're in opposite directions, you're going to get a repulsive force. So let me ask you guys this. What happens to this force in this case? Oh, and by the way, there's an equal and opposite force, right? Newton's third law. There's an equal and opposite force on the other object. You guys are Isaac and what's going on, guys? You guys just had a conversation where everybody in the class could hear you and you're calling someone dumb? That kind of behavior is like utterly unacceptable in any form. So now everybody in the channel who's not you is sitting there thinking, are they talking about me? That was really rude. And I think you owe everyone an apology. You're right. People using the N word is dumb. That is acceptable, and thank you for your apology, Isaac. I appreciate that. No, you're okay, dude. It happens all the time on the internet. I just wanted to clarify for everybody. Okay, so Same direction for the current, the force is attractive. Opposite direction, the force is repulsive. I really wish we were at school right now because we have an amazing demo for this. But I do have a demo I can show you of this on the internet. Before we do that, I just want to ask a couple questions here about this equation. What happens, for example, and I guess I should write this out. Maybe I can type it so that you can see it down here. What happens to the force between the wires if the current in each wire is doubled? I'll ask other questions to that too. About that too. Yeah, first question. So what happens to the force between the wires if the current in each wire is doubled? What's going to happen to it? Is it going to become double? Is it going to cut in half? Is it going to become quadruple? Yep, more first for sure, but how much more? So let's say that quadruple, yeah, exactly. That's right. So, yeah, if the current in the wires is doubled, then you're going to get 4 times the force. What happens to the force between the wires if the distance between the two of them is multiplied by 3? So if basically A, right here, if that is tripled, what happens to the force between the wires? You know? So this becomes 1/3. Anyway, that's the force between two current carrying wires. Now, this is the video for it. Do you guys have any questions before we keep going? This is pretty similar to the demo we have at school. Can you guys see this okay? And tell me, is there any sound? It's just static, but I'll let the video speak for itself. Okay, there's really not any sound. So there's repulsive. So here, let's back up for a second, see if you guys remember. So if they do, so you saw the repel, right? They'll do it again. See that? Our demo looks like exactly like this. It's really cool. What's going on in the wires right now? What's the direction of the currents? Like if I tell you the left one's moving up, what's the direction of the right one? Yeah, if the left one's up, the right one has to be down. They have to be opposite directions, right? Because they're repelling. And he's going to switch it so they go the same way, and you'll see that they're attracted, right? Opposite. Same direction. Oh, there's a zoom-in version. The version we have of this, like, is, basically the same thing. Okay, do you guys have any questions? This is another video of something we saw last time. All right, so there we go. A little bit of theory. Okay. So the next thing we're going to do now is we're going to talk about Ampere's law. This will be a little bit of theory, and then we'll kind of go from there. Okay, so a couple weeks ago we learned about something called the Biot-Savart law, or maybe it was a couple weeks ago, right? And the Biot-Savart law allowed us to calculate some things. One thing, for example, that we were able to calculate was this right here. Biot-Savart law allowed us to define what the magnetic field due to a long current carrying wire is, right? But the way that we did that was really quite complicated. And Ampere's law provides for a way to do the same thing. But it doesn't require like nearly as much brute force mathematics. It kind of appeals to symmetry, you might say, and it allows us to deal with finding magnetic fields in situations where using the Biot-Savart law would be quite difficult. Just to remind you guys what the Biot-Savart law was, I'll put it up right here. It said that you could find magnetic fields by doing this very complicated thing. You have to do mu naught, and you have to multiply by current, and then divide by, I think it's 2 pi. No, 4 pi. But then you have to do this really complicated integral where you take the current line elements and you cross product them with what's called r hat, and then you have to divide that by the radius squared. So this is what we call the Biot-Savart law, and it's just really extremely difficult to do much with. Ampere's law is different from this, okay, but it solves the exact same problem. It's basically a simplification of the Biot-Savart law. And I'm going to write down what it states. So it states that if I, for example, have a loop of wire, or not a loop of wire, sorry. If I, for example, have a current carrying wire, okay? So I have a long piece of wire that carries current out of the board. Okay? If I were to draw a ring around this, just an imaginary ring, okay? And I were to imagine walking along this path that I've created here. In this case, what I'm going to do is say, suppose that we want to walk along this little path here, and we want to do it in this direction, where every one of these little dashed lines represents what we call a piece of, a line element, like a little piece of arc length or something around this circle. Every one of these things represents that. Okay. Then we can produce what we call a line integral around this path here, okay? And what it would look like would be something like this. We could integrate the magnetic field around that path, a closed path like this, so a closed line integral. And what Ampere's law states is that this should be equal to mu naught multiplied by the current that is enclosed by the path. So I, E, and C represents the current, okay, that flows and I gotta be really careful about how we say this because of some complications that are going to arise later on. It's the current that flows through any surface enclosed by the path. Now this is all very mathematical, but I promise you I can explain it in a way that will be quite simple. So these little green lines right here represent your path. Okay? And I enclosed is going to be the current that flows through any surface enclosed by the path. The way we define that current is that it can be positive or negative, and it's positive when the fingers of your right hand would naturally curl in that direction. And I'll say more about that in a second, but so this is it. This is Ampere's law right here. That is Ampere's law. Now, what it's used for, does this sound the way that I've described what I just said right here, specifically this statement here? Does this start to sound like any of the other things we've learned in this class? What does this sound like to you guys? It sounds like Gauss's law, right? Where in Gauss's law, it was the magnetic flux, right? Or sorry, the electric flux was basically equivalent to the charge enclosed within a Gaussian surface. So this path right here is often referred to as an Amperian loop. Kind of similar to the Gaussian surface, except it's a line, right? So it's a one-dimensional circle, right? So we call it an Amperian loop. And the path right now, we would say enclosed by the loop, you might say, okay? Do you have a question, Hunter? Okay. Is that the one that's due next time or the one that was due this time? No, I mean, if we're actually, yeah, you're supposed to use Ampere's law for that, and we didn't get it to it before break. If you guys need more time on that homework, you can have more time. Yeah, we were supposed to cover Ampere's law before the break, but we didn't quite get there, right? Anyway, if you do need more time, let me know. Okay, let's look at some applications of how Ampere's law looks. So we can apply it to exactly the situation here to prove something really simple. Ampere's law is usually used to find magnetic field. Right? So that's what you're looking for out of here. You're trying to get that magnetic field out of there, similar to the way that Gauss's law was used to find electric field. So let's go about solving this problem, okay? So this is how this works. This is going to happen very fast, so you have to listen carefully to all the words I say. This derivation is like one line long. So what we say is that we start with the equation. We say, this is going to be my loop. How much current is enclosed by my loop? Well, it's the current that we've defined as I out. It's just the current coming out of the board, right? And now we say, okay, what kind of magnetic field is this going to produce? Well, it's a line. It's a line of charge coming out of the board. And that line of charge is going to have to produce some kind of a magnetic field. Whatever type of magnetic field it produces, it's going to have to be circular in nature. And we can probably assume that the magnetic field is going to point in the same direction as the path that we've chosen here, because our fingers would naturally rotate in the same direction as the magnetic field, right? The way you do this is you take your thumb and you point it out and you think, okay, my fingers on my right hand, right? Here's my fingers on my right hand. They would rotate naturally in a circle like this, right? If this is your thumb coming out of the board, you point your thumb in the direction of the current, your fingers sweep out the direction of the magnetic field. I know that drawing's horrible, but this is your thumb, those are your fingers, that's the way your right hand rotates, right? If you don't believe me, stick your thumb on the screen that you're looking at, right where the I out is, and sweep your fingers in that direction, okay? So experimentally, we know that's the direction the magnetic field's going to point, but there's also, from symmetry, a reason to believe that that would also be the way that it points. The biggest thing to understand now is that the magnetic field and ds are pointing in the same direction, right? That means, what does that mean about b dot ds? What can I reduce this down to? If the angle between the two of them is 0, right, b and ds are pointing in the same direction, then you get b times ds, right, times the cosine of 0, which is 1. So you just get b ds, right? In addition, and now we need to label one other thing on here, if I define this to be r, the radius of my circular path that I've created right here, then I can say that at every point on that circular path, the magnetic field should be the same. Just symmetric. It has to be symmetric, right? Which means that I can actually pull the magnetic field. Let me go back to black. I can actually pull the magnetic field out of this equation right here. Right? And then I can say, well, the integral of ds, can anyone tell me what that's equal to? Yeah, it's going to be like the arc length, right? 2 pi r. The integral of this is s, which is the length of the path, which is the arc length of the path, which is 2 pi r. And one more line and we're done. Because this tells us that the size, and again, the goal was to find b, right? The size of the magnetic field is now equal to mu naught multiplied by the current. In this case, we called it I out. It's really just some current divided by 2 pi r. This is the same thing that we got from using the Biot-Savart law, except it's extremely simple. And this is a very powerful way to calculate what we'll see in a second, the magnetic field of a solenoid, the magnetic field of a toroid as well. Okay, that is Ampere's law. And do you guys have any questions? Oh, I thought I copied this question from this other book. I did not. I could just pull the book up and show you the question. That works just as well, right? Where was it? Here we go. Yeah, this works just as well. So let me say something first before I ask the question. So if I have the following scenario, like let's say that I take you and I tell you that I've got some current right here that comes out of the board, and I say it's equal to 5 amps, okay? And I over here put a current going into the board, and let's say I call this one I1, and I call this one I2, and I say this one's like, let's say 3 amps, but I say that it's going into the board. If I do a loop around this one, and it doesn't even have to be a circular loop, as it turns out. I do any type of a loop, that's my loop right there, then as long as the loop is in the same direction as the kind of direction dictated by the current here, then this is going to tell me that the integral of b dot ds in this case just ends up being equal to basically mu naught times the current I1 in this case, so times 5 amps. But for this one over here, if I do a loop around this one, here, let's use this color. If I do a loop around this guy, this one is going to give me a negative. This one's going to end up being like negative mu naught times 3 amps. Or the better way to think about it, probably, the simpler way to think about it is just, mu naught multiplied by negative 3 amps. Okay, so when the direction of your loop is the same as the direction of your ds vector, in this case ds points like this, and the magnetic field points in the same direction, then you get a positive, and if they're opposite directions, you get a negative, okay? And so maybe you can tell me if any of that made any sense to you guys, I don't know. If I draw a loop around both of the objects, and I make it so that the loop goes like this, what will we get for that one? Can anyone tell me? Can anyone put all that together and figure this out? And again, the loop doesn't have to be circular. Yeah, it's going to be 2. Yeah, exactly. You guys got it. Because you take 5 minus 3, basically, right? This is why it's just like Gauss's law, right? So Gauss's law says, you add up the charges inside. This says you add up the currents inside. Some positive, some negative, right? Does that all make sense? So now let's ask this question. Here's the question. Can you guys all see this? I don't know if it's all working. Let me look at OBS. So look at Quick Quiz 30.3. It says, rank the magnitudes of the integral of b dot ds for the closed paths a through d from greatest to least. Okay, so you've got all of these currents. This one is 1 amp out of the board. This one is 1 amp into the board, and then this one's 2 amps into the board, right? And so your paths, right? A is this path out here. There's A, and A basically encloses all of them, right? And then B just encloses these 2. I think C just encloses the top 2, and it looks like D is this one here. A little confusing as to which one's C and which one's D, but hopefully you guys can figure it out. Can you guys do that? Can you rank the magnitudes from greatest to least? I should try this too. Try that out, and then just like list it in the, like type it out into the general chat if you could. I gotta find a pencil so I can write this out myself. 1 second. Pen doesn't work. Oh, I'm sorry, this is blocking. Okay, so there's one answer right there. See if you guys just keep going and see what you get for an answer and try to type it out. I'll give you guys a minute or two. And then... And by the way, it doesn't matter the shape of the path. All that matters is the amount of current that flows to find this quantity. Looks like Ed209 agrees. You guys all getting the same thing? That's also what I got, CADB. I got 6 amps. Let's see, yeah, C was 6 amps, D was 3 amps, A is 4 amps, and B was -1 amp. I did that kind of out of order. C is 6, A is 4, D is 3, and then B was -1, I think. Okay. Does that make sense to you guys? All right, so there's one other form of Ampere's law, which is kind of a little bit more complete. And what that form uses is the fact that if I have current, but the current is either not uniformly flowing through a wire, or I want to find the magnetic field inside a wire, for example, then the current that flows in a wire can be found by doing an integral, and it's technically a double integral of what's called current density dot product with dA. Where, to remind you guys, current density is basically current divided by area, and then it basically flows normal to the area vector, basically. So this is called current density, just to remind you guys. We haven't used it very much, but it becomes a little more useful now. And in that sense, what happens is that Ampere's law becomes, and this is a surface integral, by the way, Ampere's law becomes the integral of b dot ds is equal to mu naught multiplied by that double integral that I just wrote there. If you go look up Maxwell's equations, this is the form you're probably going to see. You'll see one of these two, but this is one of Maxwell's equations as well. And we'll talk about how we actually evaluate this quantity here, the j dot dA, with the next problem that we do. Although we're taking a break, so it won't be right now, but... Okay, that's Ampere's law, the theory behind it, and stuff like that. Do you guys have any questions? So it's 2:53. We should probably go till 55 or 3:05. And I'll stop the recording.